Whether scrolling on a phone, typing on a laptop, or watching television, you are staring directly at millions of microscopic individual pixels. Buying a new screen means wading through a thicket of marketing acronyms: LCD, LED, OLED, AMOLED, and Mini-LED. But beneath the billions of dollars of marketing, the entire display industry operates on just two mechanical philosophies. Every modern screen you look at is built as either a shutter or an emitter. Understanding how these two methods physically handle light at the microscopic level allows you to see the real trade-offs being made every time a manufacturer slaps a new acronym on a box. The shutter philosophy is the foundation of the standard liquid crystal display. In this system, a massive, brilliant white backlight is stationed at the rear of the device, firing continuously. This diagram shows the vertical stack inside an LCD. A rear polarizer filters the backlight into a uniform wave. Twisted liquid crystals rotate this light to pass through. When a transistor applies voltage, the crystals untwist, blocking the light to create a dark pixel. An LCD is an exercise in restriction. It relies on millions of tiny, voltage-controlled blinds constantly fighting to hold back a miniature sun. Because that backlight is always firing, the optical blinds can never block it perfectly. Some light always leaks through, turning what should be pitch black into a glowing, washed-out gray. This diagram illustrates Mini-LED's approach. Instead of a single massive backlight, the source breaks apart into thousands of tiny, individually controlled zones. Through local dimming, it completely cuts power to specific zones behind dark areas, halting light bleed at the source. By keeping a dedicated backlight system, Mini-LEDs can still pump out searing peak brightness, easily pushing up to 4,000 nits to make bright daylight scenes and specular highlights highly realistic. By utilizing thousands of localized dimmers, Mini-LED forces an older technology to produce both deep blacks and blinding highlights. The rival emitter philosophy, found in OLEDs, takes a completely different path. It entirely discards the backlight, the polarizers, and the liquid crystals. Every single pixel is constructed from an organic material that generates its own independent light the moment it receives an electrical charge. To display true perfect black, the screen simply cuts power to that specific pixel. It produces zero light, yielding an infinite contrast ratio. Without the need to wait for physical crystals to twist and untwist, an OLED pixel can change state in roughly 0.1 milliseconds. Emitters trade the brute force brightness of a complex optical sandwich for absolute, pixel-perfect light control and near-instant motion clarity. Because emitters are made of organic materials, they degrade over time. If a static image, like a news ticker or a health bar, is driven at maximum brightness for thousands of hours, it can leave a permanent ghost burned into the screen. For darkroom movie watchers and competitive gamers who rely on perfect shadows and instant motion response, an OLED is the clear choice. For bright sunlit rooms or users who leave static interfaces up all day, a Mini-LED provides the necessary raw brightness and total immunity to burn-in. These complex methods of light control were only made possible because of the discovery in 1888, when an Austrian botanist realized that cholesterol extracted from carrots could exist in a state that was both a liquid and a crystal. Choosing the right display comes down to matching these microscopic light control methods to the physical reality of your own room.